This is part 3 of our Forces of Nature tornadoes, excuse me, not tornadoes, earthquake interactive. At this point, we've already done pages 1 through 6. The final part is about triggering your own earthquake and seeing what happens when they're on different types of land, seeing how that earthquake's damage level, if you will, is different on 3 different types of surfaces, bedrock, landfill, and fault zone. And I said a surface, I should change that phrase. Instead of surface, let's think of it as the structure, the base, that ground type that the building is built on. Primary purpose of this third video is for those students who do not have the ability to use this interactive on their computers or whatever devices they're using at home. I would really encourage you, if you do have that ability, to go through and test out these different types at a low and a high magnitude and read a little bit about how these different ground types can impact that damage to the man-made buildings. So without further ado, let's start reading and then testing them out. Collapsing buildings are one of the leading causes of death during an earthquake. The violent shaking that occurs in the ground can cause dramatic devastation. Earthquake engineers strive to build structures that can better withstand a quake by studying the various factors that influence damage. Construction material, building structure, and foundation design are all critical elements to consider. But first, engineers must decide where to build and what size quake they are anticipating. Make your own earthquake and see the influence of ground type and magnitude size on building damage. So let's go through these in order. We'll do a bedrock at low and high magnitude, and then we'll go ahead and try the other ones. Just to orient you, we have just a model of a building here in the right top portion of the screen. And then down below where it says earthquake waves, you'll actually see what is this grid-like version of the Earth, and see how the wave moves through the Earth with this low magnitude wave in bedrock. Let's start our earthquake. So we'll see it pulsing through and see that earthquake shaking the building. And we can look at the damages. We saw a couple of windows fall out. Let's read about a bedrock with a low magnitude earthquake. Bedrock is the relatively hard, solid material that is found underneath the soil or sediment layer. If you want the best chance of withstanding an earthquake, build on bedrock. In a low magnitude earthquake, a small earthquake, the building might experience some shaking or vibration. Pictures may fall off the walls, loose objects on shelves might topple and fall over. But the structure itself is likely to remain intact. Let's see what happens with bedrock when we have a high magnitude wave. It says that bedrock is pretty strong and sturdy, but maybe with a bigger earthquake, it's not quite as durable. Let's see. Here we have a big high magnitude wave coming. And we can see it in the size of that, can't we? So observe the differences in the building here. Looks like we still had some windows cracking, and here it looks like there's some pieces of the building that have started to break and maybe fall off. Some of this is going to be the same, but I'll read it again because there is a little bit of extra information. Bedrock, the relatively hard, solid rock that underlies the soil or sediment layer, is generally the safest place to build to avoid earthquake damage. Sounds like that's still their perception. However, few buildings can escape the shaking of a major quake completely unscathed. During a high magnitude earthquake, violent shaking from the surface waves may cause damage such as cracks in the building, shattered windows, and crumbling at the structural joints. So I wonder how this is better or worse than things like a landfill or things like a fault zone. If you're not familiar with what those are, we'll read a little bit about those when we do this next little bit of the activity. So let's try a landfill at a low magnitude. At a low magnitude, this landfill area may be a little bit different than what we see with the bedrock. Oh, look at that. Okay, so I'll leave you a moment to make your own observations of this picture, but I'm going to read along over here and then point out my observations. So landfill with low magnitude. Landfill is often made of soft, loose sediment. Because landfill is frequently used to fill in areas previously submerged in water, the sediment may be wet. Landfill is one of the most dangerous places to build a structure that might experience an earthquake because it is susceptible to something called liquefaction. Liquefaction is a phenomenon where the surface waves cause the solid ground to act like a liquid. In a low magnitude quake, liquefaction might cause the ground to flow and sink around buildings. Liquefaction can also create sand boils, mini volcano like structures that spew sediment and water. In addition, structures built on a landfill may experience some sinking or slight tilting during a low magnitude earthquake. Let's try it with a high magnitude earthquake and see the differences. And I apologize, I'd mentioned I was going to make my own observations, but I think some of you saw it sank into the ground a little bit, building as that almost kind of quicksand-like material shook up and settled out. It created a pocket of space for that building to sink into, and which caused a lot more damages to it. I would assume it's only going to be worth with a high magnitude wave. Landfill with high magnitude waves. So obviously this one has a lot more damage. We saw that the building sank a little bit lower, probably because with that high magnitude wave, there's a greater shaking. And in that process, it's making that sand and sediment kind of settle out more to get more compact. Um, we see more damages to the building overall. So all this is exactly the same. I'll just quickly read it. One of the most dangerous places to be during a severe earthquake is in a structure built on landfill. Scientists sometimes compare the landfill to wet sand on a beach at the water's edge. The loose particles are solid, but when significant pressure is applied, the ground will ripple and buckle. That might have been different, actually. During a high magnitude earthquake, landfill is highly susceptible to liquefaction, a phenomenon where the ground acts like a liquid. The once solid ground is shaken at a resonant frequency and appears to move like a thick soup. Buildings can sink and topple. Liquefaction may also cause sand boils, mini volcano-like structures that spew sediment and water, and ground flows. Another danger is amplification. When the ground loses its solid strength, the waves have the ability to grow larger and cause more shaking at the surface, which in turn causes more damage. Pretty serious stuff there. A fault zone, if you will recall, either a normal fault or a reverse fault, slip strike or slip dip, whatever type of fault, there are buildings that are created on fault zones as well, which may be a good spot, maybe not a good spot. What do you think? We'll see at this low magnitude set what it looks like there. So here we have the building in the middle, actually, because it's going to show it right on that fault zone. So even at a low magnitude wave, this actually has some pretty significant damages. Let's read about it. If a structure is constructed over an active fault zone, a significant source of damage can be the actual rupturing of the ground surface. During a low magnitude quake, the rupture may be minimal and the displacement may be small, but the building still could sustain cracks and some shearing along the fault line. You can see that the ground's actually broken there underneath where looks like it slipped. And that's, of course, caused some damages up in the building itself. What about a fault zone with high magnitude waves? So in this case, a high magnitude wave is likely going to be very devastating. We can see as the building just topples, um, bits and pieces of it breaking all around. We can imagine that if there were actually people in this earthquake, that would be quite devastating. Um, whether they're walking by, whether they are in the building, a lot of very harmful results are taking place from this. So in a fault zone with high magnitude, a building constructed over an active fault zone is likely to be in tremendous danger during a major earthquake. There may be major rupturing along the fault, as well as significant displacement. If a structure straddles the fault, it can experience cracking, shearing, and displacement. Foundations and walls may tilt or rupture. Sometimes buildings may collapse entirely or partially. So that finishes out this particular Forces of Nature Interactive. We've done all 7 pages at this point if you've watched videos 1, 2, and 3 now. And I'm just going to take a moment to talk through some extensions of this. And of course, there's a variety of other things available that you could look up online. But if you are interested and you have extra time, there are the options to look at the map and also the case studies. And the map is going to show you a lot of disasters that have taken place if you're looking at tornadoes and hurricanes and all these things, but we're just looking at earthquakes. If you want, you could also go back and look at these different tornadoes, volcanoes, and hurricanes as well. But what we're seeing is earthquakes from before the 1900s up to almost the year 2000. We can move around the map a little bit, and you guys, I'm sure, are more than capable of figuring this out, but you'll be able to look at these and see kind of some of the earthquakes that have taken place. The case studies take you a little bit deeper even, allow you to look at and read a lot of information, even some firsthand photos of what this earthquake resulted in. And we have 6 different case studies here in different regions all around the world. So if you're interested in those, feel free to take those out to take your understanding of earthquakes a little bit deeper. We will dive back in next week to learn more in our own direction in 6th grade science. For now, thank you so much for your time, for all of your hard work, and we're going to call this video completed. Please reach out if you have any questions.